This is the original version of the Nano VNA. It covers 50 kilohertz to 1 gigahertz, or 1.5 gigahertz rather, but it's now also available in a version 4, which reaches up to 3 gigahertz at the high end. The Nano VNA is probably the most powerful antenna analyzer available today, and at a very affordable price. VNA stands for Vector Network Analyzer, the likes of which used to cost in the tens of thousands of dollars just a few decades ago. So why is it so powerful? Well, on its tiny screen it can display a number of antenna parameters at once, but we're going to concentrate on just the VSWR and Smith chart plots in this video. Most of us are familiar with VSWR, or voltage standing wave ratio, but maybe don't know what the Smith chart does for us. The Smith chart may look a little intimidating at first, but displaying it on the Nano VNA provides us with a tremendous amount of information. Not only does it display the radiation resistance of the antenna, but also its reactance. These are called the real and imaginary parts of the impedance, respectively. For most antennas, we try to tune them for a radiation resistance of about 50 ohms at a particular frequency, or something close to that value. That ensures a good match with the transmitter output impedance and the 50 ohm coax feeding the antenna. If that condition is met, we achieve a VSWR of about 1:1, where reflected power is near zero and radiated power is at its maximum. If, however, the antenna is cut too short for the frequency of interest, the antenna impedance now presents a capacitive reactance component. The real or radiation resistance portion of the impedance may also shift a little from 50 ohms. Under this condition, the VSWR starts to creep upward and somewhat less than full transmitter power is radiated by the antenna. Similarly, if an antenna is too long for the frequency of interest, the imaginary part of the impedance now becomes inductive. Again, this results in increased VSWR. Let's look at the Smith chart display on the Nano VNA to see how impedance is displayed. Here we're looking at an antenna that's optimized for the center of the 20-meter band. A nice feature of the VNA is that you can analyze the impedance and the VSWR over a band of frequencies you select rather than only one frequency at a time. It does this by sweeping a very low-level signal into the antenna over the selected frequency range. No more QRZ is this frequency in use when trying to measure a VSWR using your transmitter. If you're a shortwave or scanner listener, this device also gives you a way to check your receiving antenna performance without illegally transmitting and using a VSWR meter. The horizontal line running through the center of the chart is where we read radiation resistance. The left end of the line represents a short or 0 ohms, while the right-hand end is open circuit or infinite ohms. The exact center of the chart along this line represents 50 ohms radiation resistance. The Nano VNA is normalized to 50 ohms, so a perfectly tuned 50 ohm antenna at a particular frequency will fall on this spot. Intersecting the resistance line are circles. Anywhere on each circle, the reactance has a constant value. However, any point on a circle that is above the horizontal resistance line is inductive reactance. Similarly, any point below the resistance line represents capacitive reactance. In our 20-meter band example, we can see that the impedance does vary from capacitive through pure resistive and into the inductive zone over the entire frequency range. The wheel on the top of the unit will allow you to move the marker up or down in the frequency. Note that as you do, the frequency that the marker is at is shown near the top right-hand corner of the display. At the top left is the impedance at that frequency, shown as resistance, followed by a reactive component value, expressed as either fractional farads or henries. As we sweep from the bottom of the 20-meter band to the top, notice that the reactance changes from capacitive to inductive after passing through a resistive value of about 49 ohms at resonance, where the reactance is negligible. Because the antenna is slightly short at the low end of the band, it has capacitive reactance. And because it is slightly long at the top end, it has inductive reactance. At this point, we only have the Smith chart on the screen. By tapping the Display tab, then Trace, we can see that only Trace 2 is displayed. By tapping Trace 0, we can now overlap the VSWR plot over the Smith chart. Note that the VSWR value is now displayed on the top left-hand corner of the screen, while the impedance now moves to the top right. The trace numbering may vary depending on the version you have. Displayed is the 20-meter antenna performance again, and we can see from the VSWR plot that the antenna is fairly broadband, showing the worst case value at the lower band limit of just above 1.7 to 1, and that resonance occurs at about 14.2 megahertz. If we widen the frequency range displayed, the display will get a bit busier. This shows the performance of a fan dipole that has elements tuned around the 17-meter, 12-meter, and FM portion of the 10-meter band. Since we're scanning from 17 to 30 megahertz, we're going to see quite wild swings in impedance and VSWR, especially at out-of-band frequencies. I can see from this plot that my 17 and 12-meter elements may need to be tweaked a little at mid-band, but are still quite usable based on VSWR values. Well, I hope this video has given you some background to help you get up and running for measuring your antenna performance using the Nano VNA. This is not meant to be a full tutorial on using the device. There are plenty of good tutorials on YouTube already that I would encourage you to explore. If you found this useful, please give it a thumbs up, subscribe to the channel, and we'll see you in the next video.